So we're doing like applications of derivatives
Okay.
is what we're kind of focused on.
Yeah.
And I think
Like
like
optimization and related
yeah,
rates.
exactly, yeah. So if we could go over like related rates maybe,
Okay.
do some of that.
I can give you an example that I think is one of the best examples on
Okay.
related rates. It's a simple problem, and yet it's very illustrative. It's the
hmm
famous ladder against the wall. Okay.
hmm
Say you have a 15-foot ladder, and it's laying against the wall. And it starts sliding down. Now let's do it the way I normally do it. We're going to have the bottom of the ladder start slipping to the left at a rate of 2 feet per second. And we want to know what's the rate that the top of the ladder is slipping down the wall
Okay.
when the bottom of the ladder is exactly 9 feet away from the wall. Okay, and this is a related rate because we know the rate that one of the things is doing, and we're trying to figure out another rate that is not immediately obvious and does require calculus. Now, the way we're going to do this, you'll notice I've drawn it kind of on an XY grid. And what is the primary equation? If I call this x, that side x and that side y, what is the
hmm
primary equation that governs this model?
So like I just get confused like if you're finding like the area of this model or if you're
Well,
finding like
here's what we're doing. I'll go through this problem. And in other words, we have a right triangle. Anytime you have the ladder leaning up against the wall, always assume the wall's making a right triangle with the ground.
yeah.
And that's equal to 15 squared. Okay. Now, everything they're giving us is a differential. In other words, they're telling us that x is moving to the left at 2 feet per second. Well, that's telling us that dx dt, that is a rate. That is a velocity, which is a rate.
hmm
Means it's going to be a derivative. We know that dx dt is it -2 or +2?
+2.
Correct. And it's not based on the direction that it's going. In other words, normally when something's going to the left, that's a negative velocity. But we're not really talking about the velocity here. We're talking about how is x changing. Well, x is getting bigger at the rate of 2 feet per second as that thing goes to the left. Okay? So we know
hmm
dx dt. Well, if we implicitly differentiate this thing, what do we get? We get 2x. What do we get? Can you implicitly, yeah, let me have you do these. Can you implicitly differentiate that?
Yeah, so 2x dx plus 2y
Hold on.
dy.
2x dx dt. Very important to get the bottom under that because this tells us we're implicitly differentiating it with respect to time, which we want to do because the dx dt that was given to us is in terms of time.
Okay.
And then that is 2y dy dt, and that's 0. And they're saying they want us to solve for dy dt. They want the rate that that top of the ladder is falling down the wall.
hmm
And we can now solve all of this. In other words, we're going to do it when x is 9. And when x is 9, y is going to be 12. In other words, we're going to measure it at that moment in time. Solve for it at that moment in time. So if I do the math here, I get 2 times 9 times dx dt equals 2 times 12 dy dt.
Would that be a negative?
Negative.
12, 2 times 12? Okay.
Yeah, and it's since I'm taking it to the other side, I'm going to make it negative. Probably would have made more sense to take the 2x to the other side, but it doesn't really matter. And so what do I have here? I have 36 equals minus 24 dy dt. So dy dt equals minus 1.5.
Okay.
Is that the correct sign?
Yeah, because y is getting shorter.
Exactly. Exactly. Okay. That is the classic related rate problem. Now, when I was studying related rates, I had a hard time with it. And a slightly more complicated problem than that we won't do, but I'll give you, which is a real life scenario. You have a car that has just robbed a bank, headed in that direction. You have a police car chasing it, headed in that direction. The police car has a radar gun pointed at the robber's car. And this radar gun gives the speed on a straight line that the robber's car is moving away from the police car. And in this picture, that's not a constant. In our ladder problem, the length of the ladder was a constant. But in this picture, I still have a right triangle, and we'll call that Z. All three of these are going to vary as the cop car gets closer to the intersection. And the cop car we know is going at 60 miles per hour. And what the cops want to know is what's the speed that the robber's car is actually going. Because all they're able to measure is the separation of Z. In other words, their radar gun is going to give them dz dt. And that's what we're trying to solve for. Whereas the information, or excuse me, no, we know that. I didn't say it, but let's make that 50. No, let's see. Yeah, we'll make z equal to 50. So dz dt is 50 miles per hour. And what we're trying to solve for is dx dt. So again, if we set up our equation, we've got x squared plus y squared equals z squared. And then when we implicitly differentiate it, we'll have this. And we know 2 of the 3. And if you know 2 of the 3, then you can always figure out the third one. In other words, we've been given dz dt, we've been given dy dt, and we're asked to measure it at a time when they are, let's see, if I want to make this a 3, 4, 5 triangle, we'll make them 4 away, and that one is 3. We'll say miles. In other words, we want to measure the speed of the robber's car, which we can't measure directly. We have to measure it with math.
Mm-hmm.
At a certain point in time, because the robber's car speed can go up and down. So we
Yeah.
want to measure it when the cop car is exactly 4 miles from the intersection and the robber's car is 3 miles from the intersection, which makes Z 5 miles. They're separated by 5 miles.
Mm-hmm.
Now I've got this equation up here, and I can plug in for X, I can plug in for Y, I can plug in for Z, I can plug in for dy dt and dz dt, and I can solve for dx dt. Again, a related rate.
Mm-hmm. Okay.
Related by this equation that describes that triangle.
Okay.
Okay. Are you also doing optimization problems?
Yes, we are.
Let's take a look at a few optimization problems that tend to be classics. How tough are these for you? In other words, should I start with the fence up against the river?
Sure. They're not as difficult, I think, as the related rates, but I think they're still pretty difficult for
Okay,
me.
I'll do the equivalent. We have a building here. That's a house. And we want to build a corral for our animals off the end of the house. And we know how much wood we have. We have 2,000 feet of wood. So the question is how do I build that corral to get the maximum area out of my 2,000 feet of wood?
Mm-hmm.
Well, let's set it up. Optimization problems are always, you're going to have two equations. You're going to have the primary equation that is to be optimized, and then you're going to have another equation that helps you do calculus on the first equation. Let's talk about the area equation here, because that's the one we want to optimize. Area. What's the area of this corral?
X times Y.
Okay. Now we know that with optimization, we want to take the derivative, we want to set it equal to 0, and that's going to tell us maximums or minimums. Right?
Yeah.
Okay. Problem is I can't really differentiate this. I want the area to be a function of one variable only. Well, let's go over here and look at another equation. The perimeter is what? According to my
2x plus Y
2x plus
equals.
y, and we know that the perimeter is 2,000. That's how much wood we have.
Yep.
Okay? So if I solve this equation for y, I get y equals 2,000 minus 2x. Now I can take that, substitute it for y into my area equation to produce this. And now I have a function that's all a function of x. I can even write that a as a function of x is equal to that. And now I can differentiate it. Okay, first of all, let me distribute it. I'll take the derivative of that. What is it?
2,000 minus 4x.
And now set that equal to 0. And
Okay.
if you set that equal to 0, and you understand why we set it equal to 0?
Yeah, so you're finding like the maximum or the
Yeah,
minimum, right?
I have an area function here that's a quadratic. Okay, I can see that it's a quadratic before I took the derivative. And I know it points down, so it's a quadratic like that. And I'm trying to find that spot right there that would make that area be a maximum.
Mm-hmm.
Okay, I'm not really interested in what that maximum is yet, although they normally do ask for all of those. But what they're really trying to figure out is what are the dimensions of this corral to make this a maximum? Well,
Yeah.
when I take the first derivative, I'm looking at the slopes. Okay, and I want the one thing I know about maximums is they have horizontal tangent lines and minimums. I have a slope like that. I've got a horizontal tangent line there and there. So when I have a third degree polynomial like that, I might come up with two answers. And I got
Yeah.
to figure out which one's the max and which one's the min. And that involves more calculus, second derivative test, or first derivative test, and so forth. But
Mm-hmm.
if when we did the math on this, we got 500, x equals 500. So the dimensions of our corral are 500 by 1,000. And that will produce the maximum area. You might think that it would be more like this, look more squarish,
Mm-hmm.
but it doesn't. Now, this specific problem is actually a problem you could have solved in algebra because you have the math in algebra to figure out where the vertex of a quadratic is.
Yeah.
So it's all we would have needed to do was take this area equation, find out where its vertex is, and it would have been where x is 500. Okay? But when
Mm-hmm.
you get into more complicated functions beyond quadratics, for instance, if I had a cubic function over here, we don't really have any pre-calculus stuff that allows us to figure out where that is and where that is.
Yeah.
Only way we have to do it is by calculus, by taking the derivative, and that will allow us to find these things called relative extrema, which is where your maximums and minimums occur. Um, there's some other classic optimization problems. Let me just talk about one that you would not be able to solve without calculus. And that is, you've probably seen this. You have a piece of cardboard and 8 by 11. Okay? Piece of paper. Got to be cardboard there. We're going to cut out 4 corners out of this cardboard, all the same dimension. And then we're going to fold this piece of cardboard up along the dotted lines to make a open top box. You with me? Have
Mm-hmm.
you
Yeah.
seen this problem before?
No, I haven't.
Okay, then let's go through it. If you'd seen it before, I could go on, but this is a pretty good problem because for one thing, you end up with a cubic equation, and the only way to find how to maximize a cubic equation is with calculus. So, what is I'm trying to maximize the volume of the box. So what
Okay.
is the volume of the box based on my drawing?
Um, 8 minus x,
It's actually going to be 8 minus 2x
2x, and then 11 minus 2x, times 11 minus 2x.
times what? That gives me the area, but that doesn't give me the volume. I need a third dimension to get volume.
Times x again for
Correct.
height.
Correct. Okay. Now, if this one doesn't have a second equation, but it does produce a cubic. Let me see if I can do this. And then multiply all of that by x, you get 88x. What is that? That's minus 38x. So that becomes minus 38x squared. And this becomes plus 4x cubed. So there's our volume function. And it's all in as a function of x. So I can actually write it like that. And now we're going to take the derivative. I'm assuming you don't have any problems taking derivatives.
I think like polynomials I don't, but definitely like when I start getting into like logarithms and stuff,
Chain rule give you a little problem?
a little bit, yeah.
Okay, maybe we'll go back after this problem and look at that. Okay. Now, notice that our first derivative function is a quadratic, which means I'm going to find two places where it's equal to 0. In other words, if I set the first derivative equal to 0, that's going to produce two solutions. And it's notice that if x is 0, I am going to produce a minimum volume, right?
Yeah.
I don't have any volume if x is 0. So whatever the solution, I'm almost certainly going to come up with 0 as 1 and some other number as a number. Let's not take the time to solve that quadratic, but you can see that. And there's also a question here is what is the practical domain for x? What is it? And that's the only place we want to look. In other words, if we were to look at a curve, if we were to look at a graph of the volume function, then we would see that it has two horizontal tangent lines. And one of them may be outside of our effective range. What's the maximum x can be?
The maximum.
Yeah, what's the maximum value that x can be?
1.
Half of 8. In other words, if I cut out a corner that's exactly 4 inches, then it's going to come out to there, right? And then I won't have anything to fold up and make any volume because I'm going to have to cut out the same corner from down here.
Yeah.
So I can't make x any more than 4. So it's got to be less than 4 and it's got to be greater than 0.
Okay.
So maybe when I come up with my solutions here, I get, the x value occurs at -2 and 3. Well, clearly x can't be -2, so 3 would be our, and I am going to get a positive and a negative off of that quadratic.
Yeah.
No, I'm not. I'm going to get two positives. In other words, I'm going to have -76 plus 88. My signs are going to be minus, minus, and I'm going to end up with two positive answers. So I can do a couple of things. I can figure out which one is the minimum and which one's the maximum. But that'll probably become obvious based on my two answers here. My answers almost have to include 0, although I can't see how. But anyway, I think you see where I'm going here.
Yeah.
And it turns out that x is not an easy number to calculate. I mean, x might end up being some sort of an irrational number like this, something that you'd never be able to figure it out without calculus.
Yeah.
But now you have a box with the maximum possible volume that you've created. out of this 8 by 11 piece of cardboard.
Mm-hmm.
Okay, so this is an optimization problem that doesn't have two. In other words, your function that you're trying to optimize is already a function of one variable only. So
Yeah.
this is really actually a little more basic than the last one. It's just the last one, because you had a quadratic, didn't really require calculus to solve, where this does.
Yeah.
All right. Let's talk about just differentiating, because that's probably the biggest skill you're going to need to pass tests. You're going to have a lot more problems where you have to figure out how to find the derivative, I would say. Let's start with a simple one. Let's just go through all of the rules and make sure you know how to do these rules. What's y prime? Which rule do I use?
The product rule.
Okay.
So I do 1 times sine of x plus x times cosine of x.
Okay. Pretty good with that. Let's check the quotient rule. How do I take the derivative of that?
So it would be x cubed minus 1 times 2x minus 3x squared times 2x, or x squared, sorry.
All over?
All over x cubed minus 1 quantity squared.
Good. The way I remember the quotient rule is it starts with the bottom and ends with the bottom squared.
Mm-hmm.
In other words, you started with the bottom, and then you can, if you start with the bottom and end with the bottom squared, everything else has to be pretty much the top, the derivative of the top here, and then the reverse over here.
Yeah.
So you only have to remember that part of it to remember the quotient rule.
Mm-hmm.
Now let's look at the chain rule. I'm going to give you the toughest chain rule problems that I can think of.
Okay.
And the first thing you really need to ask yourself when you're going to apply the chain rule, what is the inside?
Mm-hmm.
Okay. Now theoretically, you could say this is sine x times sine x and apply the product rule. But let's make sure we apply the chain rule. Just
Okay. So it'd
now,
be
the chain rule in a nutshell says the derivative of the outside times the derivative of the inside. So the first question you always have to answer is, what is the inside?
sine of x.
Good. So what's the derivative?
2 sine of x times cosine of x.
Good. Now, if I look at this one, notice that this is slightly different, but actually it's a lot different. What's its derivative? What is its inside?
Cosine, it's x squared.
Correct.
Is the inside.
And the way you can really figure out what to make your inside is once you've done it, you got to be able to differentiate that thing. Well, I can differentiate that.
Yeah.
And I can differentiate u squared. In other words, this one becomes u squared. I can differentiate that. But if you said let u equal sine x in the bottom one, well, now you have nothing. I don't even know how to write that in terms of u. Certainly nothing that I can differentiate.
Yeah.
So in order to know what the inside is, when you plug it in, you got to be able to differentiate that. In other words, you got to be able to do dy du.
Yeah.
For starters. Because that's what the derivative of the outside means, is you're doing dy du. If I have y equals u, well, and I want dy dx, I can't take it directly. U is not x. But one thing I can do is I can take dy du, that's the derivative of the outside, times the derivative of the inside, which is du dx. And notice the du's cancel and I'm left with dy dx.
Yeah.
That's the whole concept of the chain rule, is this is really what you're doing. Okay? And you can have multiple things in the chain rule. It doesn't have to just be one inside. In other words, if I had something like natural log of the sine of 3x. Okay?
Okay.
What's that? Y prime.
So 1 over the sine of 3x times cosine of 3x times 3.
Good. Sounds to me like you understand all four of them pretty good. All four of these rules. And just to let you know, unfortunately, integral calculus does not have these same nice four rules. You can pretty much differentiate any function, no matter how complicated, with these four rules for differentiation: the product rule, the power rule, product rule, quotient rule, and chain rule. That'll handle everything. When you get to integral calculus, we wish it were that easy. Unfortunately, it isn't. There are about 10 techniques for integrating a function, and every one of them is harder than the one before it. It's much more difficult than differential calculus. But you're grounded good in your differentiation. And when you also get to integral calculus, you'll find that every single integration problem is half differentiation and half integration. So you never get away from differentiation. You're always using it in calculus. All right, so let's see. Let me see if I can come up with another optimization that's just a little bit more difficult. That equation is y equals 3 minus x squared. That is a parabola. Okay? The question is I want to put a box under this parabola, a rectangle rather, and I want to draw the rectangle that has the greatest area. Now notice I could draw that rectangle perhaps like this. That might be a bigger area. Or maybe I should draw it flatter like this. That might be a bigger area. But that's the goal, is to put a rectangle under that parabola.
Okay.
Well, how am I going to do it?
So you need, it's going to be 2x, or it's going to be volume equals 2x times y.
Okay, you're close. You said volume, you meant area.
Area.
Yeah, you're right, because this dimension, that's x. Which means the base is 2x. So it's 2x times the height of the rectangle, which is always y. And in this case, instead of y, I'm going to write what y is, 3 minus x squared. Now, the area of that rectangle is a function only of x. You can take the derivative of it.
6 minus 6x.
Set that equal to 0. Solve for x, and you get x equal plus or minus 1. And so it's at that point right there at 1 where the box is a maximum area. And in this case, the plus or minus, the minus does actually not really make sense. Looks like it might make sense because that's a negative 1 right there also.
Yeah.
But I think from a conceptual point of view, it's only the plus 1 that you use, and then you figure out that the base of the rectangle comes at plus 1 and minus 1 because x is plus 1.
Yeah.
Okay. Now, that one you were good at. Let me see if I can make it just a little tougher. This time, I'm going to have a sine wave, and I want to put the biggest rectangle that I can under the first hump of that sine wave. And this becomes considerably more complicated. It's the area of that rectangle.
It's going to be y.
Okay, that's good. Which is sine x times what? What is the base of that rectangle? What are its dimensions?
It's going to be...
You don't want to make this mistake. You do not want to say it's x.
It's x minus pi.
There you go. Now you're on the right track. In other words, we know that is at pi, right?
Yeah.
So what's that point?
Is pi minus x, right?
Correct. In other words, if I let that be x, the end of the rectangle, and that's what you want to do, then this distance here, yeah, I'm sorry, I pointed to the wrong thing. That distance right there is pi minus x.
Mm-hmm.
And by symmetry, this over here has to also be pi minus x.
Yeah.
So now the base of the rectangle is pi minus those two little endpoints.
Mm-hmm.
Minus that pi minus x and minus 2 up.
Yeah.
Okay, and that gives me minus pi plus x. I think, as the base of the rectangle.
Mm-hmm.
No. Just a second. Now I got to distribute the 2 also. It's plus 2x. Because I got down here, I've got pi minus 2 pi plus 2x. Okay, and pi minus 2 pi is minus pi plus 2x. So there's my function. Area equals sine x times minus pi, or we'll do 2x minus pi.
Mm-hmm.
Now I'm going to have to use what to take the derivative of that? Let's go ahead and do it.
Product rule. So it's going to be cosine of x times 2x minus pi plus sine of x times 2.
Okay. Now, let's see. We want to see where that's equal to 0. So I've got over here on the right, I'm going to make 0 equals cosine of x times 2x minus pi, and I'll move the other to the left, the plus 2 sine x, so that becomes minus 2 sine x.
Mm-hmm.
And now I have to solve that. How am I going to solve that?
I have no idea.
It's not particularly easy to solve. Especially since the biggest reason it's not easy to solve is there's two of them. One, you have a combination of a trig function and a polynomial.
Yeah.
That's not easy to solve. If I said x cosine x is equal to 1/2, that's tough to solve.
Yeah.
I don't have any algebraic techniques to do that. The only way I can do it well, I don't know if it's the only way. It's also tough to solve when you have two different trig functions. If I had sine x equal cosine x, that's not that easy to solve either.
Yeah.
Turns out that we know that that happens at 45 degrees, but only that. If I said sine of 2x equals cosine x, I'd have a lot harder time solving it.
Yeah.
Although, if I did have this, I could change the sine of 2x into an identity that was just cosines. And then I'd have a quadratic and I could solve it. So sometimes you can solve trig equations with different trig functions just by using identities and making them all the same function. But when you have a trig function combined with a polynomial, it's a whole different story. And the only way I know how to solve this is graph both of them.
Okay.
In other words, make that y1. What kind of calculator do you have?
The TI Inspire.
Okay, make that your first function, make that your second function, and wherever they cross, that is what x is.
Perfect. Yeah, that makes sense.
Okay, so, and yeah, that's a little tougher problem. For one thing, it's really easy to go wrong on this problem. It's really easy to call the base of the triangle or the base of the rectangle x, and you don't want to do that. In other words, you want to call a point x. The right base of that rectangle is at x. And then you have to go through all the manipulations we did to figure out what the length of the entire base is in terms of x. All right. We've covered a lot today, and you've been pretty good at all of it. So it sounds like you're doing good in your calculus class. What are you getting in your calc class?
Not great.
Really?
Like a C right now.
Really?
Yeah.
I'm a little surprised at that. I have not encountered a first-time calc student that knew as much as you do about all of this. I mean, understanding how to take derivatives and optimization and related rate problems, you can do all of those. You can do good on any kind of calculus test. Now, there are also are a lot of more nebulous problems, like applying the mean value theorem, or in other words, the mean value theorem says that if I have a continuous function and it's continuous between A and B, and I know the average slope between A and B, well, what's that? That's f of B. This is f of A. So I know the average slope of that line is f of B, the rise, divided by the run. And what the mean value theorem says is that there has to be a point C, somewhere between A and B, that the derivative is the same as the average slope between A and B. In other words, I can't get from A to B without going through a point C whose slope of the tangent line is the same as that average slope.
Yeah.
There has to be a point C. And so they can give you problems here about find C. And the way to do it is to figure out this first. That's your average slope. And then take the derivative of the function and set it equal to this average slope that you calculated. And that will find the point C that has a derivative that is the same as the slope of that line. The intermediate value theorem merely says you can't get from 20 miles an hour to 80 miles an hour without going through every speed in between.
Yeah.
There's no way you can jump over 30 miles an hour. You can't go 29 to 31 without going through 30 and all points in between. And there are not too many problems regarding the intermediate value theorem. It's more of an existence theorem. Both the mean value theorem and the intermediate value theorem tend to be existence theorems, meaning they're used to prove much higher theorems in calculus, not so much to work out real life problems.
Yeah.
I don't know a whole lot of real life problems. The only real life or the only even math problem I can think of on the mean value theorem is one like this, where they want you to find C. And that's fairly straightforward and easy. All right, what else have you been, what are you having troubles with? If you're getting a C, you must be, some of this stuff must give you trouble. Or are they just asking you real difficult questions?
I feel like it's a little bit of both. Like some of it's difficult, and then some of it I just make like dumb mistakes.
Okay. Because I've kept most of the problems today relatively easy. I mean, you can make some of these problems so much harder, both related rate problems and optimization problems. I saw an optimization problem the other day that was really good, that we don't really have time to go over today. But it was really tough is what I meant, but also clever, very clever. So anyway, Wyatt, let's stop there. And for our next session, which is when? Monday, I think? Monday morning?
Yeah, I think it's Monday.
Okay. Send me as much review material as you want to go over that you can go over in an hour.
Okay.
Okay. And it can be vector stuff, but you should be able to send it to me by even tomorrow, I would think, right? I mean, you're not going to get new material on Monday before, you don't have school next week, do you?
No, we're out, yeah.
Try to send me whatever you'd like to go over on Monday by tomorrow. And that'll give me a chance to, if I'm not up to snuff on some of the vector stuff, it'll give me a chance to try to get that way. Okay. Some of the stuff in vectors I understand pretty good. Other stuff, vectors, vectors have only been around for 200 years. They weren't discovered until the 1800s. They're one of the last math disciplines that you study that was ever discovered. In other words, calculus was developed in the 1600s, but vectors not until the 1800s, and there was quite a bit of controversy around it. Vectors, but I can understand why. They just have always been tough for me. It's almost like I have a mental block about some of them. That I have a hard time getting through. So I like it whenever I have a vector student because that gives me another chance to go through the material. Unfortunately, I usually only go through it once or twice a year with students, and it's hard for me to stay fresh on it.
Yeah, gotcha.
But if you could do that, I'd appreciate it. And come Monday, I won't call you. I will text. Now, what phone number do you want me to use to text you?
720-357-3017.
And I'll put you in my contacts list. That's your cell number?
That's my cell, yeah.
Okay. And as all I will do on Monday is text that cell phone, the meeting ID number. You'll definitely have it on your desktop now if you didn't before. And double click it, put in the 9-digit number I send you, and you'll be in the meeting.
Awesome.
Okay, you will have to unmute your microphone every time you go in the meeting. You won't have to set it on computer audio. It'll keep that setting. But you will have to unmute your microphone upon entry into the meeting. Okay?
All right. Thank you.
Talk to you on Monday, Wyatt. Bye-bye.
All right. Bye bye.